This chapter introduces the theory of functions of more than one variable. In Section 1, we will define these functions and their graphs, look at several examples, and introduce some visualization tools like level curves and cross-sections. We'll begin with functions of two variables. A function of two variables is a rule that assigns a number, called the output, to each ordered pair of real numbers x, y in its domain. The output is denoted f of x, y. Like with single variable functions, some can be defined algebraically, and these are the easiest to study. For example, if f of xy equals the square root of 36 minus 4x squared minus y squared, then f of 1, 4 is the square root of 36 minus 4 times 1 squared minus 4 squared, which works out to be 4. Let's compute a domain. We'll identify the domain of the function square root of 36 minus 4x squared minus y squared. All the rules you learned about domains of single variable functions still apply here. You can't divide by 0, you can't take the logarithm of a non-positive number, and you can't take the square root of a negative number. The only one of those that applies here is that the number in the square root cannot be negative. Let's write that down and see where it gets us. We have 36 minus 4x squared minus y squared is greater than or equal to 0. That's a pretty good inequality describing the domain of this function. In order to make it into something we can recognize, we might want to write it a different way. For instance, we can write this as 4x squared plus y squared is less than or equal to 36. Do you recognize this inequality? This describes the inside of an ellipse. Let's see a picture. If you plug any point inside this ellipse into the function, you get a valid numerical answer. If you use any point outside, the square root will be undefined. Many useful functions, however, cannot be defined and computed so nicely. Here is an example. This is a temperature function. Every point on Earth can be described by its longitude and latitude, an ordered pair x, y. We can therefore define a function t of xy, which gives the temperature at each point. Here, the values of t are denoted by color. If we go to Boston, where the coordinates are about negative 71 by 42, right here, the value of t is 50 degrees Fahrenheit. If we travel west to Michigan, where the coordinates are negative 84 by 42, the function decreases to 41. If we head south to Atlanta at negative 84 by 34, the function jumps up to a very pleasant 59. This is a very useful function with a lot of practical applications, but there is no hope of finding some polynomial or other mathematical expression that computes the temperature at every location in the country. Multivariable functions can also be used to describe digital images. A digital image is made up of pixels, each with its own color. For simplicity, we can work with pictures whose pixels are all shades of gray. Thus, to store this image in a computer, we need only define a brightness function b, which tells us the shade of the pixel at each coordinate x, y. This image has a domain of x between 0 and 687, and y between 0 and 1024, because that's how many pixels it has. As you can see to the right, I've zoomed in, and we can look at 2 pixels in particular. The pixel 339,773 is brighter than the pixel 1 space to its right. The brightness function takes a value of 158 out of 255. At the pixel 340,773, the value decreases to 127. Notice that this function differs from the previous 2 in another way. It is only defined at integer points. That means that any calculus we want to do on such a function will be an estimate at best, but we'll see that even estimates can give us very useful information about an image. The previous 2 examples visualize the functions using color or shade at each point in the plane. This is a useful tool for many real-world applications. However, we'll want a less subjective visualization, a graph. We already have the definition of the graph of an equation, so all we need to do is conscript a third variable, z, to our cause. Here is the definition. The graph of a function, f of xy, is the set of all points x, y, z that satisfies the equation z equals f of xy. For example, here is the graph of z equals the square root of 36 minus 4x squared minus y squared. We see that f of 1, 4 is represented geometrically by this height. We calculated its value to be 4, and it is 4 units above the point 1, 4, 0 in the xy plane. The same is true of every other point on the graph. The height encodes the value of the function for those x and y coordinates. Above those points outside the domain, the graph does not exist. The downside of a graph is that it can be difficult to visualize without the aid of a computer. But people have been visualizing 3D graphs since long before the computer age. One of the best tools is the level curve, which expresses 3-dimensional information on a 2-dimensional diagram. Here is the definition. The level set of a function f of xy is the graph of the equation f of xy equals c for some c, a constant. For a function of 2 variables, this graph lies in the xy plane and is called a level curve. For example, one of the level curves of f of xy equals square root of 36 minus 4x squared minus y squared is obtained by setting c equal to 4. This simplifies to 4x squared plus y squared equals 20, which is an ellipse. Here is its graph in the xy plane. These are all the points that evaluate to 4 when plugged into f. Notice the point 1, 4 lies on this curve. Geometrically, level curves are the intersections of the graph of a function with the plane z equals c. These planes are horizontal, so it looks like taking a level slice of the graph. The graph has a level curve at each height, and each level curve lies in the domain of the function, the xy plane. Frequently, we will draw many level curves on the domain. And this can give us a sense of the shape of the graph without having to produce a 3-dimensional drawing. From these level curves, I see that we have an oval-shaped hill, which rises quickly through many levels and then slows down until coming to a peak above 0, 0. In this example, we'll try to draw some of the level curves on this temperature graph. The key realization is that a level, say 25 degrees, corresponds to a certain color or a transition between colors. 25 degrees occurs at the transition between light blue and green. to draw the level curve, we'll just trace along that transition on the graph itself. It looks something like this. Of course, there are other places where it transitions. In here as well. Over here, over here, over here, even a little bit way over here. This shows us that a level curve can be disconnected. It also shows how futile it is to try to draw level curves for real-life functions. As complex as this one, at least. Here is one of the oldest examples of level curves. An altitude function tells us the altitude of each point on a map. Surveyors have long drawn level curves of this function on what are called topographical maps, and here's an example of one. How can we use these level curves to understand the shape of the ground in this region? Well, the first thing to notice is the rings of level curves indicating the ground is rising toward a peak. This is probably the top of a hill, as is this, and this, and this. We can also see where the slopes are steeper or gentler. Here, many level curves are crossed quickly, so the land must be rising steeply. On the other side of the hill, they are less tightly spaced, and the slope is gentler. Finally, there's a fairly interesting feature here. From this point, if you go in either of these directions, you'll be going uphill. Whereas if you go in these directions, your altitude will be decreasing. This is called a saddle point because it is shaped like a saddle for a horse. We don't have to limit ourselves to level planes in order to study the geometry of a graph. When we take the intersection of a graph with a plane that is not necessarily of the form z equals a constant, we call this a cross-section. Computationally, this need not be particularly difficult. If we want to compute the intersection of the graph z equals the square root of 36 minus 4x squared minus y squared, and the plane y equals 1, we just substitute y equals 1 into the equation. The cross-section is z equals the square root of 36 minus 4x squared minus 1. This simplifies to z equals the square root of 35 minus 4x squared, which is a graph in the xz plane. If we squared both sides, we would actually see that it's part of an ellipse. Here is a picture of that cross-section. It lives in the plane y equals 1, so the free variables are x and z. We can also see the cross-section to the right, where the vertical plane y equals 1 slices through the graph. The darker blue curve is the cross-section we computed. Like with level curves, taking different values of y will give us a set of parallel cross-sections, which we can use to infer the shape of the graph. Often we are given implicit equations in 3 variables. We may benefit from converting them to explicit functions of 2 variables of the form z equals f of x comma y. This allows us to use calculus techniques on them and makes it easier to graph them using a computer. Let's try this for the paraboloid x squared minus y plus z squared equals 0. First, we'll write it as one or more explicit functions. To write it as an explicit function, all we need to do is isolate z. So let's subtract terms to the other side of the equation. We'll write z squared equals y minus x squared. We're not quite there. We need to take the square root of both sides. We get z equals plus or minus the square root of y minus x squared. You'll see that we haven't quite managed to write this as a single explicit function. That's because it fails the vertical line test. To cover the whole graph, we'll need two explicit functions. Say f of x, y equals the square root of y minus x squared, and g of x, y, which equals negative the square root of y minus x squared. Now we'll compute the level curves. We'll set c, a constant, equal to this plus or minus the square root of y minus x squared. We'll square both sides. c squared equals y minus x squared. This can be graphed in the xy plane, but it's easier if we solve for y. We get y equals x squared plus c squared. This is a parabola shifted by c squared. Notice that c squared is non-negative. So these level curves are only shifted upward. Let's graph them. We can try to visualize the graph by imagining these level curves stacked on top of each other, one on each level. Do you think you can tell what it looks like? Let's pull up a model. Here's a computer model of the three-dimensional graph. As you can see, we have the level curve z equals 0, which is where it meets the xy plane. And that's graphed on the left. If we change our value of c, we can find the level curves below the xy plane. And we can find the level curves above xy plane. Seeing these curves together on the left shows how the graph rises as we travel in the y direction. Here's an exercise for you. Pause the video and see if you can apply the definitions we've covered so far. Okay, here's my solution. The first thing we need to do is take this implicit equation and write it as an explicit function. This is obtained by dividing by x. We get z equals y over x. That's an explicit function. If we want to, we can write it in the form f of x y equals y over x. Now, what is the domain of f? Well, it's the whole xy plane except we can't divide by 0. What is this? This is a line. What about level sets? Well, we set c equals y over x. If we want to understand what these look like, we should solve for y. We get y equals cx. Since c can be any number, what we have here is a bunch of lines. They have different slopes based on c, but they all have a y-intercept of 0. So our level sets look like this. They're lines of different slopes, including negative slopes. Everything except a slope of infinity, because the y-axis is not included in the domain. What does this tell us about the graph? It suggests that if we start at this level and go around this way, we will reach higher and higher levels, as these are higher and higher slopes. And the same is true here. This is a low level, and if we go this way, we reach higher and higher levels. Let's see a three-dimensional model to confirm our intuition. Here is my computer model of the graph. As you can see, the level curves, where you intersect with different level planes, are all straight lines with different slopes. The graph appears to twist around like a corkscrew as it rises. We'll take another look around it and see that twisting action. We can define functions of 3 variables or more as well. We denote them f of x, y, z, and introduce other letters if we need them. Here's a summary of what changes when we add another variable. The graph of a 3-variable function would take the form w equals f of x, y, z. This would live 4-dimensional space, so it isn't a very useful visualization tool. On the other hand, the level sets of a graph are graphs of 3-variable equations living in 3-space. Instead of calling them level curves, we call them level surfaces, and these are something we can actually picture. The fact that the graph of a function is 1 dimension higher than its domain leads to the following useful observation. If we have an implicit equation of n variables, we could try to solve for one of the variables as an explicit function of the other n minus 1. Alternately, we can view the equation as a level set of an n-variable function. For example, given the equation x squared plus y squared plus z squared equals 25, a sphere, we could solve for z and get a 2-variable function, plus or minus square root of 25 minus x squared minus y squared. But another way to approach this would be to think of the 3-variable function w equals x squared plus y squared plus z squared. In this case, the given equation corresponds to a level set, w equals 25. Both of these ways of looking at graphs will be useful to us later in the chapter. That's all we have to say for now. Here are some summary questions to consider before we start on partial derivatives.